Okay, so now we are discussing nonlinear gravity. We wanted to construct a nonlinear version of the spin 2 gravity, and the path that we were following, the rule was to find construct a covariant theory, covariant action. And the rule was to find an action which depends on, well, we said originally that depends on h mu nu and other matter fields in such a way that it is invariant on the general coordinate transformations or diffeomorphism on the x mu going to x mu plus x mu, where x is general. The general four functions, arbitrary functions. And then we said that we divide this full action into a gravitational part that only depends on h mu nu, and a matter part that depends both on h mu nu and psi. So this part vanishes if I set the matter fields to 0. That's why the decomposition is unambiguous. And then we found a bunch of rules for how to construct this matter action. We said that want this condition to be satisfied. In particular, delta xi of this matter has to be 0. And then the conditions that we found was that first of all, the h mu nu should become added to eta mu nu to form a full metric, and the action will only depend on the g mu nu in this full metric. And then we can have dependence on matter fields, but also if we want derivatives, we should have covariant derivatives. So for instance, for a scalar field, the action becomes integral d4x, the square root of minus g mu nu times d mu phi with the minus 1/2. And then if you have a mass term, there will be m squared phi squared. So here, since I'm taking derivative of a scalar field, this is just an ordinary derivative. There is no difference between ordinary and covariant derivative for a scalar. But if you want to write an action for Maxwell field on curved background, then we have to use covariant derivative. We have to use covariant derivative because a mu is a vector. Actually, it's a lie, but
what is it?
Huh?
What is it?
No, it's a lie because here actually it doesn't matter. You could use ordinary derivatives, but conceptually, this is the correct way to write it. because we are taking derivatives of derivatives of a vector. And so on. Now, these actions are invariant on the diffeomorphisms or on the general coordinate transformations. And we could verify this, for instance. Here we can actually go and by brute force verify this invariant. And we can also, it's also good to keep in mind that there are two ways of applying these coordinate transformations. There is an active way and passive way. In the passive way, you transform the measure, and then this is square root of g times d4x is invariant. But then the scalar field would not change. So phi of x goes to phi of x prime. And then the measure has changed from d4x to d4x prime. But in the active way, we don't touch the measure, but we change all of the field. So in the active way, there will be a delta phi. The scalar field will change to xi mu d mu of phi. So the way we construct the action is invariant in both ways. And again, sometimes it's easier to think about it in one way, sometimes it's easier to think about it in the other way. Like for instance, in this example, this change of, but these different ways, of course, there are some little differences, right? Here, delta phi was 0, here, delta phi was non-zero. So for instance, in this problem, when this expression for delta g mu nu that I gave you was the change under an active transformation. It would contain a term that would shift the argument of the metric. If you expand it in terms of Christoffels and look into the details, you will discover that term. Okay. So anyway, we have the rules to construct the matter action. There are, again, if you consider more complicated representations of Lorentz here, like fermions, for instance, you need extra information that I haven't given here, but it's known. There are rules to do it. We don't need it for anything that we discuss here. Now, imagine that we found this general covariant action. Then, from there we can obtain, we can define a new way to derive an energy momentum tensor. Now it's an energy momentum tensor that is defined for this gravitational theory. And it is covariantly conserved. So we can talk about covariantly conserved T mu nu. And so let me just write the final expression and then talk about why it's the relevant option. So the covariantly conserved T mu nu that we can derive from a matter action is given by minus 2 over square root of g times delta of S matter d g mu nu. And the claim is that this object is covariantly conserved. D mu of T mu nu is equal to 0. This should look very similar to what we have been discussing. Except that this is only valid when the equations of motions are satisfied. So this is right on share. Okay, now why is it the case? This is actually a consequence of the fact that this matter action that we have here is generally covariant. It's invariant on the diffeomorphism. So let us consider the variation of this matter action under coordinate transformation. So this variation has two pieces. One is that this S matter depends on the metric. So one part comes from the variation of the metric, the other part comes from the variation of the matter fields. So there are two pieces here. And now I'm going to write the action as an integral of the density, Lagrangian density here. So there are two pieces. There is one that comes from the change of G mu nu. So remember that this is, let me put an index m. So this is not the action that we were talking, the Lagrangian that we were talking about in the problem, because there we were talking about the gravitational, purely gravitational part of the action. This piece. So that part was only a function of G mu nu, while this part only depends on the matter. So this is the L hat matter. There is delta G mu nu here, but then there will be an extra term, dL hat d psi, delta of psi. And of course this is delta under the diffeomorphism. So this is the total change which has to vanish. Now in this first piece, we can do some manipulations. So this first piece, if we want to write it explicitly, delta xc of G mu nu with upper indices is just minus delta xc of G mu nu with lower indices, but then with indices raised with G mu nu, with the metric. So it is basically minus del mu xi nu minus del mu xi nu.
Why should we choose the variation to be like this? Of G mu?
You mean this term?
Yeah.
Are you asking about why?
Yeah.
Are you asking why delta G mu nu with upper indices is minus G mu alpha, G mu beta, delta G alpha beta? Is this the question?
No.
No.
I mean the original form of the G mu.
Oh, okay. In general, you're asking why this is the case. It's just a fact. G mu nu is a tensor, right? So you know what are the transformation properties of G mu nu. G tilde mu nu of x tilde is equal to dx alpha, dx tilde mu, dx beta, dx tilde nu, g alpha beta of x. Right? So if I consider an infinitesimal transformation, so call I don't know, call x tilde mu equals x mu plus x psi mu. Plug it in there and then expand to linear order in xi. Then you will get that expression. An easier way to realize that must be the answer is the following. Remember that G mu nu is h mu nu plus eta mu nu plus h mu nu. Right? And then we have the linearized transformation of h mu nu. So we knew that if we do a linearized diff, meaning that we ignore terms which depend on h mu nu itself, this is just d mu xi nu plus d nu xi mu. But since g mu nu is a tensor, once you consider the full nonlinear object, you should covariantize this expression. So that's the only expression that once you linearize it, or take to consider it at 0th order in h mu nu, reduces to this, but it is covariant. So yeah, so now we have this term. So you can notice that this is symmetric under the exchange of mu and nu. So these two terms are actually the same. We can just look at one of them. And then we can manipulate it a little bit to write it as a total derivative plus something like this. How do we do that? We multiply and divide by g mu nu, sorry, by the square root of g. And let me just keep one of them. Factor of 2 here. And then there's a minus sign. So this is equal to that. I haven't done anything. Then I can write it as the square root of minus g times del mu of x in nu times 2 over square root of minus g delta dl hat d g in nu plus the square root of minus g x in nu times del mu of 2 over square root of minus g dl hat dg mu. And now I just use the Leibniz rule. And now I can use this golden formula that I mentioned to you in the first line. So as you see, this is the covariant divergence of a vector. So this first term is just minus ordinary derivative. I can take this as square root of g inside. Ordinary derivative of x in nu times, just take 2 outside, delta L hat delta g mu nu. And then the second term, well, the second term is nothing but minus the square root of minus g x in nu times del mu of t mu nu, the t mu nu that I defined there. So now if I plug that back in here, remember this was just the expansion of the first term in this formula. So if I plug it inside the integral, this term is just a total derivative. So it's irrelevant because xc is an arbitrary function that I take it to be vanishing at infinity. So this is irrelevant. What remains is this term. Plus that last term. So there will be d4x. There is a minus the square root of minus g del mu t mu nu, no, x mu del mu t mu nu plus dl hat d c del and this is 0. So I just plug this expression in there and I drop the total derivative. Now the step is to consider when the fields satisfy the equation of motion. The matter fields satisfy the equation of motion. When that happens, then this term is vanishing. Right? So this is just an arbitrary value, some particular variation with respect to matter fields. But on the equation of motion, the variation of the action with respect to matter fields should vanish. We just variation of action on the arbitrary change of the matter field should vanish. So this is one particular variation. Therefore, this expression is 0 when the equations of motion are satisfied. Matter equations of motion. And therefore, we conclude that this term has to be 0. When the equations of motion satisfy. Which is what we mean by Einstein. Now, for instance, we can check that this T mu nu that we obtained by applying this procedure is in some explicit cases, like for this scalar field, you can explicitly check that the T mu nu that we obtain by applying that procedure is going to be the same as the T mu nu that we obtain using another procedure. In particular, if we take some action, some matter action, and for a moment pretend that we want to put it on a curved spacetime. So instead of, there is a matter action that lives on flat space, but for a moment we pretend that it lives on a curved spacetime and make it covariant using the rules that we have. And then apply that procedure. And then we set G mu nu back to eta mu nu, go back to flat space. What we have obtained is something that is ordinarily conserved. Right, so then if we go back, if we obtain something mu nu, and then we go back to flat space, this covariant derivative becomes just the ordinary derivative. And we have obtained a symmetric tensor which is ordinarily conserved. So it's a valid energy momentum tensor for the system. So this is actually very often this is a more convenient way of deriving energy momentum tensor, even if you don't care about gravity, even if you live in Minkowski. If you want to derive energy momentum tensor for an action, it is more convenient to couple it to the metric, do the variation with respect to metric, and then set the metric to Minkowski. Okay. Now, however, notice that if we are in curved space-time, so this is not ordinary concept, but covariant concept. This does not give us a conserved quantity or a conservation law. Meaning that, if you remember, before we were defining the energy and momentum as the integral over the space of the zeroth component of T mu nu. So that was in Minkowski. And the reason why that was that if I take the time derivative of this P mu, if this T mu nu, remember in Minkowski, this T mu nu is ordinarily conserved. So
This
this
can be the homework.
sorry?
Yeah, it can be the correct problem of the homework.
Oh, is it the first problem?
Okay, doesn't matter. Nice.
Go on. Well, listen.
Anyway, now I'm telling you. This would be the I of Ti mu. This is a total derivative, total divergence, which reduces to a boundary term. So if I assume everything is vanishing at infinity, then I will get 0, which means I have a conserved quantity. This procedure cannot be applied if T mu nu is covariantly conserved rather than ordinarily conserved, right? Because the 0 of a covariantly conserved quantity is not going to be.
Unless they're in with a constant gravitational field.
Right, there are some situations when you can't define conserved quantities, but generically it's not there. So generically, when we have gravity, we are in curved on a curved space-time, then we can we have this covariantly conserved T mu nu, but we do not have conserved quantities. However, at the end of the lecture, which is about now, I'm going to give you an alternative that, at least in asymptotically flat spacetimes, it allows you to calculate conserved quantities. It allows you to define conserved energy and moment. So I guess before saying that, let me just say something about the gravitational part. So we said the total action has a matter part, which we now understand what to do with it. And then there is a gravitational part that is a function of h mu nu. So and again, it has to satisfy that condition. It has to be covariantly. Sorry, it has to be covariant, generally covariant. It has to be invariant on the general coordinate transformation. Again, the same as before. It cannot be. It cannot depend on h mu nu. It should really be a function of g mu nu. This combination, and also its derivatives. So there are a number of conditions that this has to satisfy. One is that delta xc of xc has to be 0, and secondly, very importantly, it should reduce to the linearized or quadratic action that we derived for h mu nu. So we had some linearized theory of the spin-2 gravity. We wrote an action, a quadratic action for that. And that has a nice Newtonian limit. It works well when we are in the weak field regime. So whatever nonlinear theory that we write, it has to reduce to that when we go to the weak field regime. So at quadratic order, this is G quadratic has to go to what we had before, which was something like I think it was something like 1/32 pi g integral d4x h mu nu epsilon mu nu alpha beta h alpha beta. So this epsilon mu nu alpha beta was a differential operator, with second order differential operator that we introduced. Which means that whatever we write here, at least it should contain a piece that is second order in derivative. So it's a two derivative terms that it has a two derivative term that once we go to quadratic regime, it reduces to that, and the answer, there is a unique answer to this conditions. The two derivative general covariant term that we can write is called the Einstein-Hilbert action. Now I'm not going to prove it in this lecture. Later we will have the tools to see why this is the unique answer to the question.
You can have higher powers of R, I think.
You can have higher powers of R. They satisfy this condition for sure. But this condition, there will be some
Modification.
There will be some, either they start at quadratic in HV nu, then there will be higher derivative corrections. So at line distances, they are unimportant. Or they might even start at higher order in HV nu, so they even don't appear in this second order. So yes, the answer is that you can add them, but following the general rules of constructing effective field theories, we want to the most important terms that are large distances are the ones with the lowest number of derivatives in them. So you can, and generically you do have higher order terms in here, but as long as you care about the physics of large distances and large time scales, those are unimportant. There will be small corrections to what you derive from the original one. So there is no...
Large distance compared to what?
That's a good question. There is a length scale here. Moreover, when you write that higher order terms, if you write R squared terms, no, but for higher derivative terms, you will also need to introduce extra mass scale in the problem. But at least here, there is one length scale. Sometimes there are other length scales in the problem that might be important in the comparison, but at least the most direct answer is that here we introduce a length scale which is called the Planck scale. And large means that larger than the Planck scale.
Okay. I think that when you have the higher orders, it's like modified gravity models, huh?
No, I mean it's just gravity. It's just, I would call it just a normal gravity. It's an effective field theory and it can have higher derivative terms in.
Okay.
There are other kinds of modifications of gravity, but I guess we don't need to discuss them. No, there are. These would be just terms that become important at microscopic scales, at very short distances. That's why we don't care about them, because we want to see.
If they are not, they would be even normal. Okay, I don't know if that would be a good question in this case. Like you have higher order kinetic terms, that would be normalizable, but okay, anyways, we don't care about that in this classical theory.
Well, already this action is not renormalizable.
Yes.
So that's not a worry for us. We are working with effective field theories. There are other modifications of gravity that are changing the behavior of gravity at large distances. Like imagine if instead of massless spin 2, I talked about massive spin 2. then that's an infrared modification, because at distances larger than the mass, the behavior of gravitational force is dramatically modified if the graviton has a mass, right? You know that if the force carrier has some mass, then the potential or the force that you get will be exponentially suppressed at distances larger than the mass. You will get a potential that will go like e⁻ mr over r. So these are called infrared or long distance modifications of gravity. That's a different story. We don't have any reason to do these modifications. And usually these modifications introduce some theoretical problems in the model, which are, I would say, they are still unresolved. So that's not, you don't need to worry about those either. Now, this action that we wrote here, which is generally covariant, now we can follow similar steps. So this, you should think of this as an L hat G, which only depends on the metric. And if we do a variation of this action to find the equation of motion for the metric, it gives us, so the variation of this action gives us 1 over 16 pi g delta L hat delta g mu nu. Now, if we do this variation, let me also divide by the square root of g. This we will show later. Actually, sorry, before that, I haven't said what this R is for those who don't know. This is called the Ricci scalar. And Ricci scalar is trace of the Ricci tensor. And Ricci tensor is the trace of Riemann tensor. Riemann tensor is not the trace of it, as far as I know. But it has to do with the curvature of the spacetime. But we will talk about them later in more detail. Just keep in mind that this R is a scalar quantity that only depends on the metric. And it is a scalar in the sense of general covariance. On the coordinate transformation, it transforms like an ordinary scale. Now, when we do this variation of this action, what we get is something that is called the sorry, let me do. So let me put 2 here, and this will convert to 2 pi g. No, actually, that's. So this is just 1 over 16 pi g, some tensor that is called the Einstein tensor. And indeed, this Einstein tensor is, when I linearize it, it gives me this epsilon alpha beta mu nu h mu nu. With the factor of the factor of 2, I believe. So that we can check. Oh, by the way, this Riemann tensor, again, that I forgot, is made out of the derivatives of the metric, right? So this is R mu nu alpha beta is equal to d alpha gamma mu beta minus d beta gamma mu alpha plus gamma mu alpha lambda gamma lambda mu beta minus gamma mu beta lambda gamma lambda alpha nu. So some combination of these Christoffel symbols. As you see, Christoffel symbols had one derivative of the metric. So when I construct this object, you see that every term in this construction has two derivatives. So it has two derivatives. It's a two derivative action that I'm writing. So it has the right number of derivatives as this linear as that. Of course, it's a fully non-linear term. And so if I take this action and derive the equation of motion from it, so let's add now the full thing. We have S gravitation plus S matter. This is the total action. And let us take the variation of this total action with respect to G mu nu. And let me do the following. Multiply by 2 divided by square root of minus G. So I get the part that comes from the gravitational action. This is 1 over 16 pi G. Or 1 over 8 pi G times delta L hat G divided by delta G mu nu 1 over square root of minus G. This is what I get from the variation of this term. And then from the variation of the matter action, I will get minus from the variation of the matter action, I get minus. This is basically how we define T mu nu, right? Except for a minus sign, I believe. So this is minus T mu nu. And then we set it to 0. This part we call it G mu nu is actually related to those quantities. R mu nu minus 1/2 G mu nu times R. And then the equation of motion that we get will be this. This G mu nu is equal to 8 pi G times T mu nu. Now I think I have missed the sign somewhere because I was expecting a minus sign on the right hand side. But that I guess we can fix later. So I can only say that when I linearize this G, okay, now I get the right linearization. This is actually 1/2 times epsilon mu nu alpha beta times H alpha beta. Up to or minus sign, we recover a linearized order, the linearized equation that we had before. So this satisfies that condition. I guess the rest we can discuss later. Any questions about this?
When you linearize the mu, you will get many factors.
Compared to the linearized matter T mu nu? No. But one way is to, I haven't proven. One way is to check explicitly in some example. Right, I just take for instance the action for a scalar field and see that my definition and the original definition using another current is going to give the same answer once you put the metric to Minkowski without any coefficient. But the general reason is that these two procedures are not totally independent, right? When we did another procedure, remember what we did was that we took a translation, used the fact that the action is invariant on the translation, and then promoted the parameter of translations to a space-time varying function. But here, when we derive this T mu nu, we are essentially doing the same thing. So that they are not really independent. Okay. Other questions?
How about when you have the action with R squared? Isn't that in some inflation model? Or remember how to call it?
The Stravinsky.
Uh-huh. What are the consequences of that? Like having an R squared there.
Well, that action you can actually map it to a theory with a scalar field coupled to metric, and then it becomes an ordinary, a typical inflation model with a scalar field which has a potential, with a particular kind of potential.
The same as Lovrov? No?
Yeah. Yeah, but with a particular potential.
Okay.
You can have, so you have a slow roll inflation, but the shape of the potential is, it has to satisfy some constraints which are called the slow roll constraints. But other than that, the shape is not fixed. You have some freedom. So Stravinsky corresponds to a particular shape of that potential.
Okay.